Okay, good afternoon and happy Monday. So we're back online. And I'm getting that I'm muted, which I'm kind of confused. Can someone let me know if you can hear me? I think we're good.
Hear you.
Okay, good. Thank you. Okay, so just a couple of reminders. Start with modeling homework is due tonight at 11:59. The interim report is due April 6th. And actually, I've opened up the first set of homework for control technologies, and that'll be due on April 8th. Also, just a reminder that participation question is open on Friday through Sunday, and there'll be another participation question this week. Don't know what it will be yet, but there will be one. So, having gone through modeling, the last real unit that we'll talk about, or major unit that we'll talk about, is control technologies. So we'll start with control of primary pollutants. And these include materials that are produced during any sort of manufacturing process. They could be produced during a milling process, during construction activities, mining operations. They include anything, material from asbestos, maybe they can include heavy metals, flour, sugar, grain. We don't think about those as particulates, but in a large factory, those actually are a significant cause for concern. They can also be metal filings. So we're just concerned about these for a number of reasons. They're toxic. Many can be small enough to be respirable so that you can breathe in. They make it all the way to the lungs. And one of the biggest problems is that they're highly flammable and explosive. I'm going to show a video, and this is pretty graphic. It's about 5 minutes. We'll show about 5 minutes of this. But I want you to have a sense of when we're talking about particulate removal, and we're really focused in a manufacturing setting, what we're talking about, and the importance of both proper housekeeping. Some of you may end up working in an environmental health and safety aspects of the industry, or you may end up in some sort of a manufacturing facility. So, like I said, a show about 5 minutes. This is pretty graphic, but I think it is important to get this sense.
I need fighting now. It just blow up. It just blow up. I need all 5 units to the sugar refinery now. It's a whole fire. It blow up.
At 7:15 p.m. on February 7th, 2008, a violent explosion erupted at the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Surveillance cameras in the area captured the blast, which took the lives of 14 workers and injured 38 others. The Chemical Safety Board launched an investigation. The fuel for the blast? Combustible dust.
Combustible dust can be a catastrophic hazard in American industry. 3 of the 4 most serious accidents that we've investigated have been combustible dust explosions.
In 2006, this pattern of accidents spurred the CSB to issue a comprehensive study of combustible.
Okay, I'm not quite sure what the problem is because I can see it on my screen and it's not projecting. So I'm not quite sure what is happening right now. Somebody can let me know what you're seeing, because this video should be should be showing, and I'm not quite sure why.
We can see it. It's just not like the entire screen.
Okay, but is it actually moving? Because I have it on I have a laptop and it's not, it's just frozen on that.
Yeah, it's moving.
Okay.
The fuel for the blast?
Thank you.
Combustible dust.
Combustible dust can be a catastrophic hazard in American industry. 3 of the 4 most serious accidents that we've investigated have been combustible dust explosions.
In 2006, this pattern of accidents spurred the CSB to issue a comprehensive study of combustible dust, which uncovered 281 fires and explosions that had occurred over the previous 25 years. The study revealed what the CSB called a significant industrial safety problem. Combustible dust fires and explosions continue to occur frequently, fueled by accumulations of combustible dust, which can gather over years in hidden places or in plain sight.
No company wants to see its facility blown up and destroyed and its employees killed, but they just don't understand what the hazard is. They don't realize that they have a hazard here until that one day when the explosion occurs, and it's a terrible tragedy for them. And they look back and say, if we'd only known.
When Tammy Miser got a phone call late one evening in 2003, she worried it would be about her brother, Sean Boone, who worked at an automotive parts factory.
And we usually don't answer the phone that late, but we knew when it kept ringing that there was something wrong, so we answered it, and there had been an accident there before, so I knew. I knew they were calling me. It was my brother.
Sean Boone was a mechanic at the Hayes Lemmers plant in Huntington, Indiana.
I got to go around the corner, man.
The company produced aluminum car wheels. The process of finishing the wheels left behind aluminum scraps, which were chopped into small pieces and sent to a furnace to be melted and reused. Chopping, drying, and blowing the dry chips through the transfer piping created highly combustible aluminum dust, which flowed through ducting to a steel drop box outside the building, where large particles were trapped. The air then entered a dust collector, which removed finer aluminum particles. Over time, aluminum dust accumulated inside ducts. In addition, there were leaks in the piping used to transfer aluminum chips, which caused dust to build up on surfaces throughout the furnace area. Aluminum dust landed on beams, ledges, and equipment. In some places, the dust was several inches deep. On the night of October 29th, about 10 minutes after workers started the aluminum chip melting process, aluminum dust inside the dust collector was suddenly ignited, perhaps by a metal ember or impact spark, resulting in a large explosion. The blast propagated back through the duct into the steel drop box, blowing it apart. The fireball and pressure wave continued back through the duct system into the building, gaining intensity as the accumulated aluminum dust ignited. The violent disturbance shook loose dust that had built up on external surfaces. At about 8:30 p.m., plant mechanic Sean Boone was one of several workers in the area of the furnace. Without warning, a fireball erupted from the furnace, engulfing the area and igniting airborne dust in a second, larger explosion. The explosion blew a 50-foot wide hole through the roof of the building. Co-workers found Sean Boone.
Okay, we're going to stop there. I know that, as I mentioned, that's pretty graphic, but I want you to, like I said, I want you to have a sense of when we're talking about explosive dust, we're talking about particulate removal. This is what we're talking about. We're talking about particles like were mentioned in here, particles of flour grains, they can be metal filings, and it's important that we find ways to ensure that they are removed properly, and that we maintain a safe environment. So when we look at these device removal of these particulates, we'll look at basically two different types of processes. We'll look at what are referred to as wall collection devices, and we will look at what are referred to as dividing collection devices. Back in the, if you think through that video, they happen to mention the drop box. There's actually a drop box on your right, and what was on the left where the spark ignited were actually cyclone separators. Basically, these are two processes that are using gravity and centrifugal force to remove particles. We'll also talk about electrostatic precipitators. These are using electrical current, charging particles, and then they get removed along a wall. And then we'll talk about dividing collection devices, and these include filters and scrubbers. So in all cases, what we're looking at is we've got some sort of solid particle. We're looking at moving that particle, moving to some sort of a wall. And then it, in some cases, will actually form agglomerates. So we've got larger particles as these particles attached to one another. They hit the wall and then they are removed, and they may be disposed at that point or reused. So first process we'll look at are gravity settlers. These are just simple devices. If we look back at, I'm trying to go back to that video. But if you look at that video, it's basically just a simple device where you're allowing particles to settle. So you've got some sort of a large area, lower velocity of your gases, and that allows particles to settle out. These are simple to operate. They typically are manually cleaned, some sort of regular interval. Because they have little moving parts, they require very little maintenance, low capital costs, low energy and maintenance costs. They're reliable. The big problem is they're large. You need to be able to slow those gases down to very low velocities in order to get particles to settle. And they're often used for very dirty gases, so pre-cleaning, and then because they don't have the highest collection efficiency, but they're used for pre-cleaning, and then those particles can go into a secondary process. So this is a image of a gravity settler. We have gas flowing in here. Notice the cross-sectional area of this duct is much smaller than the cross-sectional area of your drop box. So, and then again, the cross-sectional area of the duct leaving is again much smaller. So you've got a higher velocity in this initial duct, much lower velocity as that air moves into this drop box or gravity settler, and then a higher velocity as it leaves. Now, it's not shown here, but we can add baffles. So for instance, we can put in baffles here. We can put in baffles here. Basically what we're trying to do is we want to distribute that flow so that we don't want flow just through the middle. We want flow distributed across that drop box. So essentially we're using the entire cross-sectional area. Otherwise we would have short circuiting, and you'd see significantly reduced removals. We'll talk about two different velocities. We'll talk about a horizontal velocity, which is along the length. And then we'll also talk about a settling velocity of the particle, which is in a vertical direction. So here what you see is a simple drop box. You can see here is our dust-laden airstream. So we've got air flowing in. You've got air movement. Again, you've got a much larger area, so your velocity is significantly decreased. You have particles then falling out, and they can be discharged either to be reused or to a waste stream. And then we have a may have another treatment process after that for further removal, or can just go back into the process. And you can see here, these are just 55-gallon drums that are used to collect the dust in this case, and then it is just recycled or wasted. So as I mentioned, what we're assuming is an average horizontal gas velocity. So this is your flow, so Q, so we flow in through that duct, divided by the width times the height. So if you look here, you can see the width, and then here's our height. So that will give us the average horizontal velocity. We'll make a few assumptions here. We're going to assume that the horizontal velocity in that chamber is constant everywhere. So it doesn't matter whether we measure the horizontal velocity here, in the middle, here, wherever, okay? That velocity is the same, so that really means that we have good distribution, even distribution of the gas throughout that entire cross-sectional area. We will also assume that this vertical component is the terminal settling velocity. So difference, this pertains to the gas, and this pertains to the particles. So your terminal settling velocity is a function of the particle. Your average horizontal velocity is really a function of the gas. And then we'll also assume that if a particle settles, it's not re-entrained. So it moves, settles in this drop box. Once it's settled in the drop box, it's not re-entrained, remixed, and then moves with the gas. Now, in terms of plug flow, if we have, kind of think of this as our drop box, and we have gas flowing in and gas flowing out. Okay. If we have true plug flow, what we can do is we'll draw, so this is a parcel of gas. And that parcel of gas is going to move through the reactor, okay, sequentially. So you can kind of think of it like a railroad car moving down the tracks. There's no mixing of particles from one as it moves down, okay? It just, a particle of air just moves down down the drop box. Now, we're assuming that within this drop box, within this parcel, we have good mixing. So within that, we have an even concentration. Our gas is just moving down, okay? And that's our plug flow. So we're going to assume we have plug flow. We'll introduce a correction for variations from plug flow But that will, as a general rule, what we're really assuming is plug flow. Now, we're going to make an assumption now here. Okay, so a particle, we're going to think about a particle entering the chamber at some distance above the floor. And really a parcel of air. So think about this. Let's change this to parcel. So this is our parcel of air. Okay, so our gas parcel of air enters, okay, and it's going to take time for that parcel of air to traverse the chamber. So if we can start here, if we look back at this, we've got this parcel of gas entering here. It's got to traverse this to get to the other side, okay, and eventually out here. The time that it takes for that parcel to traverse the chamber is simply the length divided by that horizontal velocity. So that's the time that it takes for this parcel. Now the particle, so get back here. Now let's draw a particle with let's use a different color. Okay, so we have a particle here. And what we're looking at is we're looking at the time that it takes for that particle to settle. And the time that it takes for that particle to settle is equal to the height divided by the terminal settling velocity. And just kind of remembering this terminal settling velocity, if we have a particle and it is settling, we have a drag force and we have the force due to gravity, and where acceleration is equal to 0, that is our terminal velocity, settling velocity. So this gives us again, this is the time. So we're thinking of it as a time that it takes for that particle to settle. So if we take both of these equations and we take the ratio of the time that it takes for a gas particle to settle divided by the time that it takes for your particle to settle, and we just equate these, then what we have is we have an equation here in terms of our general parameters. Okay, so we have measurable or design parameters. So we have length, terminal settling velocity for the particle itself, divided by the height and the horizontal velocity. So essentially, this is going to give us an efficiency. And if you kind of think about this, I've tried to describe this here. So we have different particles. So, and all of these particles actually, the way I've drawn them, essentially, they have essentially the same terminal settling settling velocity, but where they enter is going to have a significant impact. So these particles here can escape. They come here, they move, and they actually escape. So those particles are not going to be removed. These particles here, the red ones, are captured. Now remember we said that those would not be re-entrained. So if you can think about it here, if, for instance, if it takes 10 seconds for the gas particles to traverse, but it takes 20 seconds for your particles to settle, you're going to get 50% removal, okay? If, on the other hand, it takes 10 seconds for the gas to traverse, but only 5 seconds for these particles to be removed, what does that mean? actually have, in that case, 100% removal. It can't have more than 100% removal. So think about that when you're working these problems. When you're doing the homework problems, if you get a percentage greater than 100%, the answer is 100% removal. You can't remove more than 100%. So the fraction captured is what is that equation that we just used. So this will give us our fraction captured, and this is assuming plug flow. Okay. We can then use Stokes' law. So what do we use Stokes' law to determine the terminal settling velocity. We now have introducing terms for gravitational acceleration, the density of the particle, the density of the air, so Stokes' law is temperature dependent, times the particle diameter squared, divided by 18 times the viscosity. So we actually now have an equation for the percent removal that's in terms of all of these parameters. Number of things to remember. With this, okay, is we can in some cases, because in most cases your density of your particle is much greater than your density of air, you'll actually see equations where this term is assumed to be essentially zero because it's so much smaller. Number of things also with the Stokes' law, we're assuming spherical particles. We're also assuming no interactions between particles. So when particles are settling, if they do collide with one another, think of it as an elastic collision. They don't attach, they don't grow, they just simply collide and then separate. And then we will assume uniform distribution of particles across the inlet. Okay. So those are the basic assumptions. And then we can use this to calculate the percent removal. We can also use a mixed flow model. And that means that we actually have some mixing in that X direction, but we don't have mixing in the Z direction, but not in the X direction. And that's going to decrease efficiency. So basically, particle may come in at some height, but because you have mixing, it ends up higher in your drop box, and it's less likely to be removed. So if we have this mixed flow model, then we can use this equation here, which this is the efficiency of the mixed flow model. Okay, so we're going to make sure here this efficiency has to be in a fractional, not a percent, but a fractional amount. So where we typically use gravity settlings are with particles that have a terminal settling velocity greater than about 13 centimeters per second. Particles, you can use it for particles greater than 50 microns. If your density is low, that's about 1.5 grams per centimeter cubed or kilograms per meter cubed. And if it's higher density particles, or more dense particles, you can remove smaller particles. So basically, your removal efficiency is dependent both on the particle size and the density. Typically, you're going to want uniform and relatively low velocity, as I mentioned before. Often you're going to want it less than about 30 centimeters per second. So that's why you need a large volume. In the video that we watched, you saw the settling in the duct work. Well, why? Because you've got this large volume, particles then potentially have that chance to settle out. And then we want to operate this in a laminar flow regime, so we want a Reynolds number less than about 2,000. So we can do a couple examples, and I'll add a slide in here. So let's go back and look at this. So what do we have? We have gravity settler. It's operating at room temperature, ambient conditions. It has a height and a width of 3 meters, so those are the same, and a horizontal gas velocity of 20 centimeters per second. First thing we want to do, we're going to determine whether the airflow is laminar or turbulent. So let's go here. So we have a situation, we have a height equal to 3 meters. We have a width equal to 3 meters. We have an average velocity of 20 centimeters per second. It's 20 over 100 centimeters per meter. So that is 0.2 meters per second. And Reynolds number is equal to the density of the gas times the average velocity times the height over u. So room temperature, as mentioned in the previous slide, air has a density of 1.18 kilograms per cubic meter. Velocity is 0.2 meters per second. Height is 3 meters. And we divide this by 1.86 times 10 to the minus 5 kilogram meters per second. And that is about 38,000, which means we have what type of flow? Okay, so we have turbulent flow, which means we're not going to get very good removal. So with this type of a situation, if we reduce the average velocity to 0.01 meters per second, so 1 centimeter per second, that would achieve a Reynolds number of about 1900. We would have laminar flow. But that flow, the problem with that is that that velocity is actually too low to be practical. So in a situation like this, we would probably need to think of some other process. We'll actually look at, on Wednesday, we'll look at centrifugal settling, and you'd probably move to something like centrifugal settling. If you do have turbulent flow, then you need to use the hydraulic diameter. And that is equal to 4A, 4 times the area divided by the wetted perimeter. And in this case, it would be 4 times the height times the width. divided by 2H plus 2W. That would be our wetted parameter. So for this type of a reactor, this is really what we should be using. But note that in either case, we'll have turbulent flow. So removal of particulates would be quite inefficient. So let's look at a situation here. Okay, similar situation. We're looking at if we were to design this gravity settler, we want to obtain 90% removal. We have particles 50 microns in diameter. These particles have a density of 2 grams per cubic centimeter. We've got an average horizontal velocity of 20 centimeters per second, and the chamber is 3 meters high. So if you know, that's essentially what we had before. Okay. So now the question is, if we were to use this system for these particles, how long would it have to be in order to achieve 90% removal of these particles? So let's add another slide in here just so we have more room. So we're looking at 90% removal. We have particles, the diameter of the particles are 50 microns. The density of my particles are 2 grams per centimeter cubed. The gas velocity is 20 centimeters per second, and the height is equal to 3 meters. Okay. We need to convert to meters. To kilometers per meter squared, and again, meters per second. So if we calculate the terminal settling velocity, that is 9.8 meters per second squared times 50 times 10 to the minus 6 meters times 2,000 kilograms per meter cubed, and we'll divide that by 18 times 1.86 times 10 to the minus 5. The viscosity is given. And that is 0.146 meters per second, or about 15 centimeters per second. So it's about 15 centimeters per second is our terminal settling velocity. So the length is equal to the removal efficiency, H V average over VT, and that is 0.9 times 3 meters times 0.2 meters per second divided by this terminal settling velocity. And that is 3.7 meters long. So roughly 12 feet or so. Okay, so if we have mixed flow, N is equal to 1 minus E to the minus N plug flow. So this is our mixed flow. And that, if we solve this, ln of 0.1 is equal to VTL over the average height. And so if we simply plug that in, length is equal to 9.5 meters. So you're looking at roughly a 30-foot long drop box, which is extremely long. And for this situation would be impractical. So what would we do? At this point, we'd have to, again, look at some other, most likely some other process. We'd probably switch, if we wanted to maintain the settling with a similar type of process, we would probably use a centrifugal settler. I've also included this slide here. It just allows you to approximate the terminal settling velocity. So you can see we've got different densities and a spherical particle diameter. And for instance, if you have a particle of, what did we have? We had 50 microns. That's actually not on this one. Let's say we have 10 microns. You're just going to read this up here. And then in this case, it's a density of 1, and then you'll read across. Okay, and that'll give you the terminal settling velocity. So you can use this, or you can use the equation, Stokes' law. All of non-kappa problems are actually coded with using Stokes' law. I'm not going to start centrifugal settling today. We'll do that on Wednesday. So we'll end early unless you have any questions.
I had a few questions about the homework. I don't know if you want to jump on office hour Zoom or keep on this one.
You know what? Why don't we jump on office hours and then we won't be recording?
Okay.
Okay.
Sounds good.
I'll post the notes, but that way it's not recorded
Okay.
on here.
I think Emma's going to join us as well.
Okay. Sounds
All
good.
right, cool. Thanks.
And anyone else wants to join for office hours? I think what I'll probably do is do office hours with the tablet so that I can draw pictures and we can hopefully work that way. But any questions about gravity settling? The office hours is at 1 o'clock or 2 o'clock. We end at 1:30. For some reason, my tablet is an hour behind, but yes, we'll have office hours in about a half an hour. Okay, and then I'll use my personal, it's a different link, so just make sure you check that. Okay, and I'll be online and happy to work through any of the homework problems. Where is the office hours homework link? Is in an email, is in the email. I will send it out. Once I finish this, I'll send out by email the office hours link, just so you've got that, and just to make sure that everybody has office hours link. Okay. Any other questions? Okay, so anyone will, in about a half an hour, about 1 o'clock, I'll be back online, and we will resume with questions about the homework. So I'm going to stop recording and talk to people then, talk to all of you or whoever wants to be online then, or on Wednesday. Take care and stay well.